Hi folks, we're going to talk some about electromagnetic waves. Now, light is a very, very special type of wave. There are lots of different kinds of waves. There are, of course, water waves, there are sound waves, and there are things like earthquake waves. But these are not light waves. A wave is energy that is pulsing back and forth in some sort of a rhythmic manner. Electromagnetic waves are very unique and very special and really cool and nifty. Electromagnetic waves are produced by an oscillating or changing electric field and an oscillating or changing magnetic field. Here is a sketch or a drawing of what an electromagnetic wave looks like. If you ever take a physics course that really explores electricity and magnetism, you'll go into this in great depth. But all electromagnetic waves have a collection of properties in common. So let's start talking about these. Electromagnetic waves come in various sizes. They are all the same thing. It's sort of like they're all pasta. And if you start talking about pasta, you have big pieces of pasta that are like lasagna noodles, and you have tiny little pieces of pasta that are little bits of shell macaroni. They are exactly the same thing. The difference is the size. You have big ones and you have little ones. And because of those slight differences in size and properties, pasta works differently and you use it in different locations and different dishes. Well, the same thing works with electromagnetic radiation. The long wavelength electromagnetic waves are radio waves, and we are talking AM waves, if you listen to your AM radio, and then a little bit shorter are FM radio waves. Then there's microwaves, the kind of microwaves you're going to have cooking food in your microwave oven. Right in this area, there is also going to be your cell phone. Your cell phone actually has a microwave size, a little bit longer than the microwaves in your oven, but real similar. There's infrared radiation, which are given off by everything that is warm or has heat to it. There's a very small part of the electromagnetic spectrum that is visible, that you and I can see with our eyes. Then we go to the shorter, smaller electromagnetic waves. We have things like ultraviolet. This is what gives you a sunburn. There are X-rays when you go to the doctor and they want to look inside of your body. And then there are gamma rays, which are the shortest of all the electromagnetic wavelengths. And each one of these has slightly different properties, and each one's interesting to astronomers. So let's talk about some of the properties that all of these waves have in common. All of them travel at the speed of light. Okay, and these things that they all have in common, you definitely have to know for quizzes and tests. So they all travel at the speed of light, which is 3 times 10 to the 8th meters per second. So that's 3 followed by 1, 2, 3, 4, 5, 6, 7, 8, 300 million, 300 million meters per second. That is like nutty, crazy fast. That is also the same as 186,000 miles per second. And this is the fastest thing known. We do not know of anything that travels as fast as light. So it is as far as we understand at the moment, the fastest thing in the universe and the speed limit of the universe. This is the speed of all of these waves in a vacuum. So when I say all of the electromagnetic waves, what I'm saying is that radio waves and visible light and X-rays all travel at this same speed. To give you an idea of how fast really fast is, let's take a look at this. If something was traveling at the speed of light in 1 second, so if I go 1/1000, okay, 1 second of time, a beam of light could travel around the equator of the Earth 7 times. Yeah, that's pretty quick. As I mentioned earlier, the sun is 8 light minutes away, about 8 minutes for light to get from the sun to the Earth, and the moon is a little over 1 light second away. So Things that are very far away take some time. Well, all light takes time to travel, but any light that's close to you, it happens so fast, it's hard to measure those differences. Second property of all electromagnetic waves is they travel in straight lines. And we count on that. If I am looking at an object with my eyeballs and I see that an object is over here, maybe it's a flower pot full of flowers, I can reach out and grab the flower pot and touch it because I am used to the fact that light travels in straight lines. This is how you and I maneuver around our normal everyday life. We count on the straightness of these waves. But the beautiful thing about this when it comes to astronomy is these waves will come a very, very great distance from outer space to the Earth, to you and I sitting on the Earth. And if we backtrack that straight line, that's where that star, that's where that planet actually is. How long will these electromagnetic waves travel? Well, they're going to travel forever until they encounter or hit something, until their energy is actually absorbed by something like your eyeball or absorbed by something like a leaf on a tree. This property that they travel forever in straight lines means that we can see light waves that are literally billions of years old. And in the world of astronomy, billions of years old is what we're talking about many, many, many times. The third big property of all electromagnetic waves is that they can travel through empty space. Nothing else can travel through the emptiness of space except electromagnetic waves and, of course, gravity. And we will spend a lot of time talking about gravity later. But those are the only two things that can travel through the vast emptiness of the cosmos. Heat can't travel that way. Sound waves certainly cannot travel that way. There's a whole bunch of different methods and things of energy that can't do that, but electromagnetic waves do. And I misspoke a moment ago, and I better clean it up before I make a mess, and that is I said heat can't travel through empty space. It can when it is in the form of infrared radiation, which we'll talk more about in a few minutes, but it cannot when you're talking about other forms of heat. When you look at the electromagnetic spectrum from one end to the other, from the big radio waves to the small radio waves on the other end, there are three properties that each wave has. Its wavelength, with Greek letter lambda being the symbol, its frequency, how fast or quickly it oscillates up and down, and the amount of energy that that wave carries. The radio waves on one end of the electromagnetic spectrum have very, very long wavelengths. They oscillate with a very low frequency, and hence they have a low quantity of energy. You need to remember that the three L's go together: long wavelength, low energy, low frequency. And that is the radio waves. As you go from one end of the electromagnetic spectrum to the other, there is a transition from long wavelength to short wavelength. So if you go on the far right-hand side, very, very short wavelength waves, they have a high frequency of vibration. They go up and down very, very quickly, and they also have high energy. And this is why things like X-rays and gamma rays, if they are handled incorrectly, can actually do damage to human beings and can hurt people. That's because they are very high energy electromagnetic waves. Now, astronomers look at all of these. This is a picture from NASA's Solar Dynamics Observatory showing our sun in a whole bunch of different wavelengths. This one is looking at the sound waves, actually. Sound is the wrong thing to say. When I saw a Dopplergram, that sent me in the wrong direction. We are looking at vibrations in the sun here. They are looking at the magnetic fields of the sun here. The photosphere, this is the outermost layer of the sun that we actually can physically see when you look up to it. And this is in the visible light spectrum. Each one of these other photos has a number next to it in angstrom. See the A with a little O above the top? Those are angstroms. So this photo was taken in 1700 angstroms. This is what the sun looks like when filters filter out everything but that one wavelength of light. This is 4500, 1600, and you can see different wavelengths of light. Scientists look at something like a star with all of these different wavelengths of light because each one gives them different information. So the entire electromagnetic spectrum is used by astronomers because they each help tell us something different. All right, we're going to stop talking about electromagnetic waves right here. And what we're going to do next time is we are going to start talking about how astronomers use each individual type of electromagnetic waves.